In previous lectures, we've talked about alpha, the probability of an unlikely event that occurs under the null hypothesis. Now we're going to talk about alpha in a little more formal sense, and we're going to introduce his evil twin, beta. These are also called type 1 and type 2 errors. Let's see how they work. Alpha, the type 1 error, is the probability of rejecting the null when you should not reject it. That is, you've got bad data and it makes it look like the research hypothesis is true. Beta, type 2 error, is the failure to reject the null hypothesis when you should. Again, you've got bad data, but it looks like the null hypothesis is the situation at hand and that the data does not support the research hypothesis. Power is the complement of type 2 error. Apparently, most scientists don't like to talk about bad things, so this is a probability of a good thing rejecting the null when you should. We can calculate beta, actually the z-score for the beta, by taking a close look at this diagram that shows the relationship between the null hypothesis, the research hypothesis, the critical value, okay, alpha, this dark blue area, and power, this pale blue area. We can also rewrite this equation that's used to calculate the z-score for beta and get an estimate of what the sample size is that's required to give a desired type 1 alpha or type 2 beta error. Let's look at an example and see how this works. I have a test. Public health researcher studying obesity among male university students. Her research hypothesis is that men have weights exceeding 68 kilograms, so greater than 68. Previous studies say that the standard deviation is 5 kilograms. She wants to detect a difference of 1 kilogram, in other words, mu alpha minus mu 1, mu naught, equals 1 kg. So we want an alternate mean of 69 kilograms. She collects a random sample of 100 students and tests the hypothesis at 5%. What's the power of her test? Well, let's do some calculation. We'll find the z-score for that beta. So let's see, exceeds, this is on the high side, that's why that's written as 1 minus alpha. So we've got our z beta. Subtract off the difference in the means, the absolute difference, divided by basically the standard error. And so we'll do the arithmetic, and we'll get a z-score minus 0.355. We'll look that up in the z-table to get beta. And so beta is about 0.361. Its complement, the power, is 0.639. Usually, we want power greater than or equal to 80%. So this may not be what's needed. A researcher shocked. Power is too low. Yes, too low. She wants her test to have a power of at least 85%. For the same population, how big must her sample size be to conduct the same test with the same alpha, 5%? So, if power is 85%, beta is 15%, we'll do a backwards lookup in the z-table, 15%, and get a z-score of minus 1.04. Then, we'll go ahead and calculate the sample size. So we'll take the absolute values of the two z-scores, square the sum, multiply by the variance and divide by the square of the difference in the means. So there's my 1.645 for 95%, my minus 1.04 for 15%. The variance was 5 squared. Difference is 1 squared. And we get 180. Now, why do I get exactly 180? Well, these funny looking brackets mean round up always. Since you can't have a fraction of an observation. Let's do a couple more. So what's the power? I'm determining whether human brain volumes increased in the past 20 years. Published data indicates average female brain volume is 1120 cc's with a standard deviation of 70. I hypothesize that volume's gone up to 1150, and I want to test a sample with 25 women. So let's figure out what the power of my test is. Z beta, well, I'm setting at 5%, so 1.645 minus the square root of n, so 25 square root divided by sigma, which is 70, times the alternative, 1150 minus 1120, 1.645 minus 5 over 70 times 30. Little calculator work shows this to be minus 0.50. And when we look that up in the Z table, we get a probability of 0.31. So power is 1 minus 0.31 equals 0.69, which is a little weak. So we might want to find a suitable sample size. If we'd like the power to be 90%, then the Z for 10% works out to be minus 1.28. We can check that out in the normal table. And then N, well, let's see. We're going to have 1.645 plus the absolute value of minus 1.28. We're going to square all that. Our standard deviation was 70. And we'll put that down as our difference. Our difference, I believe, was 30. Let's check it out. Gives 46.6. Of course, we're going to round that up. We need a sample size of 47.